Okay. You know what an indeterminate form is? I think that is a no. Okay. Well, now way back, we told you just to memorize this one. What's the limit as x approaches 0 of sine x over x? Okay, so we just told you to memorize it, right? And I looked at the graph, and you can see from the left and from the right, it was 1. Hey, I haven't looked for anything. Do you see them?
Yeah, somewhere between now and the last 3 places I went, right? This place is
Shoot. Okay. That's right. Hope you find them. Okay. Well, the problem right now is if we plug in 0, right, we get sine 0 over 0. And what is sine of 0? 0. So we end up with 0 over 0. That's an indeterminate form. Indeterminate forms come in a lot of different ways. I'll make a whole list for you. Determinate forms. The most common that I usually see are 0 over 0 and infinity over infinity. Okay, the others could include 0 times plus or minus infinity. And these infinities, by the way, can also be plus or minus. 1 to the infinite power. You don't see these last ones as often, but just be aware. 0 to the 0 power. We will say any number to the 0 power except 0 itself is 1. But 0 to the 0 power, indeterminate form. Infinity to the 0 power, and infinity minus infinity. So the first two, this one and this one, are really the ones you'll probably run into most frequently, I think. The others are also considered indeterminate forms. So we have this guy, L'Hopital, who found a way for us to attack an issue where it can limit the indeterminate form. And it's pretty quick, simple. I did the AP test with the 3 who showed up on Saturday. And there was one problem. I was like, oh, L'Hopital's rule. I did L'Hopital's rule 3 times and got the answer. So we had, Amisha, Yisu, and Jake. Okay. Maybe we'll take a minute later and tell about your experience. They did the 2014 test, so it's the most recent test we have. Okay, well, first of all, I'm on the wrong page now. Shoot, I closed my book. Essentially, you just take the derivative of the numerator and the denominator separately. And sometimes you have to take the derivative over and over. I think it's 9.2 I need. And you'll eventually get there to the derivative. So if you're L'Hopital's rule, okay, the limit as x approaches a of f of x over g of x. What you can do is take the limit of the numerator separately. You don't do quotient rule. Okay? What's the derivative of f of x? F prime, so that one's separate. You do not do quotient rule. And the derivative of g of x is g prime of x. Okay? And that's given that g prime of x doesn't equal 0. Okay? So, back to example 1, if we apply L'Hopital's rule, The limit as x approaches 0 doesn't change, but we take the derivative of the numerator separate from the denominator. What's the derivative of sin x? Positive cosine. Wait, so when you're taking a derivative, the ones that change signs are the cos. Cosine changes signs, cosecant changes signs, and cotangent changes signs when you're taking the derivative. So the cosine x, what's the derivative of x? 1. Okay? Now if we plug in our 0, once we plug in a 0, remember we drop the limit sign. So when as x approaches 0, cosine of 0 is 1 over 1, which is 1. Okay. So we don't have type notes this time, so this is handwritten. We're doing L'Hopital's rule of indeterminate forms. This helps us with the limits when we get like a 0 over a 0 or infinity over infinity. Okay. So let me give you another one here to try. That one, yeah, okay. Example 2. And the limit as x approaches 4 of x squared minus 16 over x minus 4. Limit as x approaches 4 of x squared minus 16 over x minus 4. If you would try to plug in 4 right now, we'd get 16 minus 16, which is 0, over 4 minus 4, which is 0, indeterminate form. Okay? So yes, you could look at the end behavior, you can look at the quadratic and the linear graph and see where it goes when you hit 4. But we can also use L'Hopital's rule. L'Hopital's rule is so easy as long as you do it correctly. Okay, correctly means you take the derivative of the numerator separate, you take the derivative of the denominator separate. Don't try to do a quotient rule. Okay? What's the derivative of the numerator? Okay. And what's the derivative of the denominator? 1. So now if we plug in, we get what as the limit? 8. Boom. You like that? And it's pretty sweet. And make sure that's a lot easier. Let me give you this one to try. Okay, this is a harder one. Sometimes you have to take the limit over and over until you finally pop it out. But we'll do some easy ones first. The limit as x approaches infinity, okay, of 4x squared minus 5x over 1 minus 3x squared. Why don't you try that by yourself? Make sure first you actually get an indeterminate form. If you're not getting an indeterminate form, you cannot use L'Hopital's rule. So it has to be one of the ones that we listed. Okay, so when we plug in infinity at the beginning, what is 4 times infinity squared minus 5 times infinity? So infinity minus an infinity. And in the denominator, well, in which infinity is larger? The positive infinity or the negative infinity? So it'll end up being some positive infinity. And the denominator, 1 minus 3 infinity squared, I mean negative infinity, so we have an indeterminate form here, infinity over infinity. So the limit as x approaches infinity, let's apply L'Hopital's rule. I like to put a little L apostrophe H, so I know I'm doing L'Hopital's rule. The reader would know you're doing L'Hopital's rule too. Okay? And what's the derivative of 4x squared minus 5x? It's what? Oh, it's not squared. Oops. 8x minus 5. And the derivative of the denominator. Negative 6x. Now, when we plug it in, plug in infinity, do we still have an infinity over infinity? Okay, so that means we need to go again. Because this could have been your first, the beginning of the problem, which if we had an indeterminate form on this step, it means we can apply L'Hopital's rule again. Limit as x approaches infinity. Okay? So the derivative of the numerator would be 8, the derivative of the denominator would be negative 6, so we get 8 over negative 6, which is negative 4/3. Now think about another way, what? Yeah, think about the way we learned how to do this problem earlier in the year. This only works with the infinity when this goes to infinity. John, what did you guys do?
We did the power.
The end behavior model. So there's another proof that this works. End behavior model works with limits as x goes to the infinities. You can take the highest power of 4x squared over negative 3x squared. The x squareds cancel out, and we get negative 4/3. So in this case, that was actually the faster route. But we can show you with the L'Hopital's rule, doing it again, you still get the same answer. Okay? Okay, let's try another one. Example 4. The limit as x approaches infinity of e to the x over x squared. The limit as x approaches infinity of e to the x over x squared. I don't remember. Maybe that was when I did L'Hopital's rule. I just know there was one. I did. Okay. What is e to the infinity? Well, e to the infinity is infinity. X squared, or infinity squared, is infinity. So yes, now this is an indeterminate form. So as long as it's an indeterminate form, we can apply L'Hopital's rule. Make sure you do not do the closure rule. This is not what this is. Do the numerator separate, the denominator separate, taking the derivative of both. Rebecca, what's the derivative of e to the x? So you put it the same. That's a nice one, right? And the derivative of x squared. 2x. So, what do you get when you plug in infinity? Indeterminate form, right? So what are you going to do? You do it again. Because this could have been your original. As long as you have an indeterminate form, you can apply L'Hopital's rule again. Limit as x goes to infinity. What's the derivative of e to the x? E to the x. What's the derivative of 2x? So this time we get infinity over 2. So what's your answer? Infinity. Which actually makes sense, right? Because e to the x goes up to infinity, and x squared also goes up to infinity. So if you combine the two, even with division, still going to go to infinity. Okay? Now I have another one. Okay, throwing some trig here for you guys. I want you to try this one all by yourself. Example 5. The limit as x approaches 0 of 2 sine x minus sine 2x over x minus sine x. First, you have to actually verify it's an indeterminate form. You either get infinity over infinity or 0 over 0. So we'll rule only works with quotients. Okay, yeah. That'll be undefined because division by 0. So fun one, huh? But you should be seeing every time you do L'Hopital's rule, your function's getting easier and easier, like simplify, right? How many times do you have to do L'Hopital's rule? 3 times. Yep. That's 6. Mm-hmm. Okay, so sine of 0 2 sine of 0 minus 2 sine of 0 is just 0. And 0 minus sine 0 is also 0. So, L'Hopital's rule to make sure you're doing your chain rules correctly. The derivative of 2 sine, Alex. 2 cosine. Oops, I forgot to see. Okay. The derivative kind of negative sine 2x. Because this 2 comes from the derivative of the inside, multiplying it. Over, let's see, 1 minus cosine x. Okay, we plug in 0. Plug in 0. Cosine of 0 is 1 times 2. We get 2 minus cosine of 0 is 1 times 2. We get 2 minus 2, which is going to be 0. Cosine of 0 is 1. 1 minus 1 is 0. So you see 0 over 0, which is an indeterminate form, you have to apply L'Hopital's rule again. The limit, and since we should be writing this limit every time until we actually plug in 0, you don't drop it. Until you substitute in, you don't drop. Okay, you can see what's the derivative of the numerator there. The only derivative of any cos, negative. Okay, and keep going. Yeah. Okay, Misha, derivative of the denominator? Oh, sine. Yeah, you're right. The sign needs to change, and then that will become a sine. Yes. And Misha, the denominator? Positive sine x. Okay, putting in 0, same thing. We have 0 plus 0 over 0. So third time should be the charm. The limit as x approaches 0. Take the derivative. Jake, what's the derivative of the numerator? Qx, yeah? Okay, and derivative of sine is cosine. You can already tell that the denominator is going to be a 1. That's good news. The numerator, negative 2 times cosine 0. Cosine 0 is 1, so that will be negative 2. 8 times cosine 0. So 8, negative 2 plus 8 is 6. Found another one? These are fun, huh? Okay. Example 6. Limit as t approaches 1, we got into an arrow, of 5t to the 4th minus 4t squared minus 1 over 10 minus t minus 9t cubed. 5t to the 4th minus 4t squared minus 1 all over 10 minus t minus 9t cubed. You can get ambiguity to check your answer. How about that? Actually, no, you can't do ambiguity model. Tell me why. It's going to 1. You can only do ambiguity model going to the infinities. So look at your work, trying to find out why. Should be 27, right? Bring the 3 down, should be 27 squared.
Are there ones that you have to do that?
Probably. And if you put it up, the numerator up to a t to the 11th power, the denominator up to a t to the 10th power, yeah.
Wait, how many times does this do this?
2, I think. Just 1? Oh, no, you're right, it is 1. And then you plug in, and that's the third step I'm looking at. Okay, so, when we plug in 1, we have 5 minus 4 minus 1, which is what? 0. Then I have 10 minus 1 minus 9, which is 0. So that's an indeterminate form. So we have to apply L'Hopital's rule. The limit as t goes to 1 of 20 t to the 4th minus 8, t cubed, all right, minus 8t over negative 1 minus 27 t squared. Okay, when you plug in 1, what do you have in the numerator? 20 minus 8, which is 12, in the denominator, negative 1 minus 27, which is negative 28. Simplifying, we have, so 3 over negative 7. Yep. Okay. Now we're going to change it up. I'm going to give you a one-sided limit. 10 plus 7. Are there any questions on that example 6 that we just did? If you didn't get negative 3/7, did you find your error? Find the limit as x approaches 0 from the right of x natural log x. Now, natural log, what do we know about the restrictions of natural log? All x's have to be positive. Yeah, this is the graph of natural log, right? Okay, so it makes sense that we couldn't approach 0 from the left. Have to only approach from the right. Now, if we plug in 0, what do we get? Plug in 0, we get 0 times, what's the natural log of 0? Natural log of 0. We have an asymptote, so it's infinity, negative infinity. Now this is an indeterminate form from our list, right? But L'Hopital's rule only works on quotients. So we have to manipulate this into fractions. How can we make this into a fraction? So we have a numerator and a denominator. Okay, we have a product here. L'Hopital's rule doesn't work on products. It works on quotients. So we need to make one of these. There's two functions, right? There's a linear function, there's natural log function. We need one of them to the numerator, one of them to the denominator. Let's not take the derivative yet, because we can't take the derivative until it's set up as a quotient. Okay. X to the negative 1, bring it down. Or you could write it as 1 over x in the denominator. Good job. Okay. So now, if we plug in, let's make sure it's an indeterminate form. Natural log of 0 as from the right. Or then as you approach 0 from the right, you're going to go down to negative infinity over what? What is, what does this graph look like? What does the graph y equals 1 over x look like? Are you sure it's 0? That's what the graph looks like. I'm just looking at this graph by itself. Okay, and since it's the denominator, well, I guess we could even just look at it as the linear x times the 1 over x. As you approach, since this is the denominator, we have to flip, and it actually approaches negative infinity. So it actually becomes negative infinity over negative infinity. Well, I was just saying what's 1 over x look like. That's this denominator. The denominator is 1 over x. X to the negative 1 is 1 over x. So it is an indeterminate form, so we can apply L'Hopital's rule. The limit as x approaches 0 from the right, so we can't equal 0. Okay, what's the derivative of natural log x? 1 over x. And what's the derivative of, this one's probably easier to think of as x to negative 1. What's the derivative of x to negative 1? Negative x to the negative 2, which is the same as the limit. Since I'm not putting in yet, I have to keep the limit 1 over x divided by negative 1 over x squared. Okay? That looks pretty messy. If you do some work, how do we divide by a fraction? Flip and multiply. Copy the first times flip the second. Negative x squared over 1. What does that clean up to? Make sure it's just x. Negative x. To the right of negative x. So what's our answer? Plug in 0 now. You get 0. Yep, all that for 0. Yep. Okay. Let's do a couple more, a bit more difficult ones. Example 8. Well, you know, this paper, that's a state function. Okay, the limit as x approaches negative infinity of x e to the x. Right now, if we put in, what would we get? Negative infinity plugged in for x would be negative infinity with the product times what's e to the negative infinity? No. What does an e graph look like? No. What does an e graph look like? Where is e going as you go to the left? Negative infinity. 0. So we have a product. An indeterminate form, that's a product. We have to manipulate it into a quotient in order to use L'Hopital's rule. Okay. So what should be my numerator? What should be my denominator? Yeah. Over and 1 over x, or you can do x to the negative 1 power if that helps you with the next step. Okay, now e as it goes to negative infinity is what? 0. Okay, remember the graph y equals 1 over x. Where's this graph going when it's going to negative infinity? 0. Okay, so L'Hopital's rule. So that's the derivative of the numerator and the derivative of the denominator. Negative x. Yeah, that's better. Okay. I'll let you keep going from there. Keep working out till you find the limit. So anyone know what the graph 1 over, let's do positive x squared looks like first. This means the negatives are positive. So if we have y equals 1 over negative x squared, but either way, when you're going to negative infinity, you still have a 0 over 0, right? So you have to do L'Hopital's rule again. And again. And again. And again. And again. And again. Now, if you keep doing L'Hopital's rule, I'm going to show you what it should have to be. Hopefully you're getting a little frustrated. Let's see. The next one would be e to the x over 2 over x cubed, or 2x to the negative third. The next one would be e to the x over negative 6 over x to the fourth. And it's just getting worse and worse and worse and worse. Okay, what do you think that means? It means you chose the wrong function to be in the numerator. Doesn't mean that limit doesn't exist, or it's infinity or something like that. It just means you chose the wrong function to be in the numerator. So let's pick a different function. Start over. Your life will be a little easier. Okay, the limit as x approaches negative infinity, so for e, let's put x in the numerator. And e to the x in the denominator. X over needs to be 1 over, or e to the negative x, right? Okay. Oh, that's good. That's good for you. Okay. Make sure it's actually indeterminate form. Look at your first function. That's a linear. As you go to negative infinity, you're going to get a negative infinity. Your e function has been flipped. Normally it's growing up. So now it's growing down. You go to negative infinity. Oh, I did that backwards. The negative is in the function, not in front of the function. If it's in front of the function, it flips down. If it's in the function, it flips horizontally. So instead of going up, It'll be a decay like that. There we go. Okay, to infinity. So L'Hopital's rule, we're doing it as x approaches negative infinity of 1 over, what's the derivative of e to the negative x? Negative e to the negative x. Now we have a 1 in the numerator, so that should be good news for you. That e to the negative x is this graph. Now we're going to do the negative function of e to the negative x. So it needs to flip down. So it's going to look like that. So as x goes to negative infinity, what do we get? So what's the answer? The denominator of negative infinity, it's what? 0. Because the denominator is getting, well, you're dividing essentially by a bigger number, but the whole thing's negative. Okay, so when your denominator is larger, 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 it's going to 0. Okay, one last one. Which example number is this? Thanks. Okay. The limit as x approaches infinity of x to the 1 over x. If you plug in infinity, we get infinity to the 1 over infinity, which is infinity to the what power? 0. When the denominator is large like that, you get 0. Is that an indeterminate form? Yes. So we can apply L'Hopital's rule in a second, actually, because first we need to have it in quotient form. You cannot apply L'Hopital's rule unless it's in quotient form. Okay? So our function, so let's start back here, is y equals x to the 1 over x, yes? Exactly. You can natural log both sides. So natural log y equals natural log x to the 1 over x. Okay. We have a power rule. How does the power rule help us here? What is the power rule of natural logs? This power gets multiplied in front. So we have 1 over x times natural log x equals natural log y. Okay? So now this time we're going to look at the limit as what was it? X goes to infinity. Instead of our y function, it's our natural log y function, which is the limit as, do we have a numerator and denominator now? Okay, what's the numerator function? Natural log x. And the denominator function? Just x, because right here, our x is in our denominator. Okay? So we plug in infinity into natural log x. And the x is in indeterminate form. Yep, it's going to be infinity over infinity. With these ones, we should be able to do L'Hopital's rule pretty quick. Limit as x approaches infinity. Ethan, what's the derivative of natural log x? 1 over x. And then we do the derivative separately for the denominator, which is well, natural log y is this. So we just use substitution. So they're equivalent. Okay, so we have to divide by 1, so it works out really nice. Just 1 over x. And if infinity is in the denominator, 1 divided by infinity, you're going to get what as your limit? 0. Okay. Okay, so for the rest of the time, you're going to be practicing multiple limits, and I'm going to give you some review problems on regular limits. Next Tuesday is your presentation with your group. Hopefully you've already brainstormed at least a little bit. So the group in charge of group 1, notice the proposal is on that, so you should be covering it. I'd also like you to add in, remember you're supposed to do 3 to 5 minutes on each subject. They're labeled 1, 2, 3, or whatever, 8, 9, 10, 11, whatever number you have. 3 to 4 minutes on each of those, or 3 to 5 minutes, doesn't say 3 to 5 minutes. Okay, and it'd be nice if you gave us a little quiz at the end to make sure with some harder problems, not just easy problems, harder problems to make sure we remember it all. Yeah, so the rest of the class, this comes from 9.2, which is on page 454. We're going to look at multiples rule 2 through 40 even, and then do some regular limits review from the chapter 2 review, 2 through 40 even as well. And maybe I'll do 3 through 39 multiples of 3. I like that better. Multiples of 3. Okay? Did you all bring your books?